In this video, we will learn about the magnetic field due to a current in a solenoid coil. Okay, so a solenoid coil is a coil of large number of turns of insulated copper wire wrapped closely in the shape of a cylinder. So this is a copper wire. So it is, as you can see, wrapped around in a cylindrical fashion around to form a shape of a cylinder. Okay. Now, alternatively, a solenoid consists of insulated copper wire wound closely in the form of a helix having a large number of turns. So this is the way you can define a solenoid in your examinations. Generally, the length of a solenoid is much greater as compared to its diameter, and the turns of the copper are wound on a hollow cardboard tube AB as shown in this particular figure. So when these two ends of a solenoid coil are connected to a battery, as you can see, the ends are connected to a battery. This is a battery, this is a key, this is a variable resistant rheostat, and this is the ammeter. And this is where the circuit get completed. Now, as a result, when you turn this key on, when you plug this key, you will see that the circuit will start, the current will flow, and as a result, a magnetic field is generated inside the solenoid as well as around it. And the shape or the pattern of the line are as follows. As you can see, these are the same as that of a bar magnet, but there is a slight difference. These are the fields, like emerging out from the north pole and merging back into the south pole, making a complete closed loop. Okay. So as the electric current in each circular loop of solenoid coil follows, so as the electric current in each circular loop of solenoid coil flows in the same direction, magnetic field of all the loops are added up, and as a result, magnetic field inside the solenoid coil becomes a strong field, and the field pattern is similar to the pattern around the bar magnet. Now, depending upon the direction of current flow through the solenoid coil, one end of the solenoid behaves like a north pole, like this, and the other would behave like a south pole. Okay. Now, the ends of the solenoid coil, where current is seen to be flowing in clockwise direction, act as south pole, and where it would be acting like anti-clockwise direction, we will consider that north pole of the magnet, as shown in this particular figure. So the current is in clockwise direction. We will learn it that it is the south pole. So this is how we remember this particular thing. Okay. Now for the north, you have to make like this. This is a way to remember. Okay. You can develop your own way to remember this, but this is how conventionally we remember this particular thing. Now, the magnetic field inside the solenoid are in the form of parallel straight lines. This signifies that the strength of magnetic field is same at all points inside the solenoid. Other words, magnetic field inside a current carrying solenoid is uniform magnetic field. So now let us study about the strength of this magnetic field inside the solenoid. So the strength depends upon the following factors. First one is that if higher is the amount of current flowing, higher would be the magnetic field. Okay. The second would be if the number of turns of a solenoid you are increasing, then the magnetic field strength will also increase because they'll all add up. Okay. But you can also reconsider this as if turns in a solenoid coil are wrapped more closely, then we can also say that a stronger magnetic field is produced. Okay. Third would be if a rod of soft iron is introduced as a core material inside the solenoid coil, magnetic field generated inside the solenoid increases by a large factor. But remember, the field may increase to even more than 1,000 times of the original value without the iron core. The fourth point is that the magnetic field of a solenoid does not depend upon the dimensions of the solenoid, as we know that the length of the solenoid is much greater than the diameter of the solenoid. So the dimensions of a solenoid doesn't matter. I hope this topic is clear to you. Thank you.